Hi, everybody. How you doing? Welcome to Lecture 9. Woo! Our last lecture before our first midterm. So this is the last material that will be covered on the midterm. So please feel free to take lots of notes, take screenshots of anything on this actual lecture, and make sure to bring the screenshots of any material you're not sure about from this lecture. Paste your screenshots directly into our Jamboard sessions, and we can work on those, your questions, as opposed to the ones that are popping up in the actual presentation. So like always, just make sure to get your questions answered. That's the key to having fun and success in Orgoland. Woohoo! Okay, so as you can see, my dog Luna has been looking for Newman the cat. Oop, I kept mentioning cat so much in the last lecture video that my dog kept coming downstairs looking for what cat? What are you talking about? So I might just call him Newman's from now on, and we'll have to, the joke will be in with us. Okay, before we get into rings and looking at rings and the stereochemistry of rings, I just want to make one thing a little clear for our next lecture. Please, for lecture 10, please try to build this four-colored tetrahedral carbon for our next lecture video, because that will be a little different kind of unique stereochemistry that is going to start popping up in chapter 7. And we're going to want to take a look at what does it mean to have 4 different groups attached to a carbon. Okay, cool. All right, then let's dive in to 3D about rings. What about rings? Enough of chains already. Let's keep playing with 5-membered rings. And if you look and build a 5-membered ring with your model kit, one of the things you'll notice is that if it is planar, it has a little 108 bond angle, which isn't too awful from tetrahedral, which is 109. So, but the issue is if it's planar, then all of these bonds with all these electrons are in the same plane, and therefore they are all repelling each other, and this causes for a great deal of torsional strain. So 5-membered rings are very popular in nature, but they are not going to be planar. So what 5-membered rings do in nature to alleviate some of this torsional strain is they take one end of their molecule and they just bring it up. Okay, so they just pull that end up into what now looks like the envelope shape. Remember envelopes? Envelopes, snail mail, all that kind of stuff. If you've ever still gotten a letter handwritten, congratulations. I love letters. But in this video, we're going to refer to the envelope of our snail mail as a 5-membered carbon. And it just pulls one side up, and what this does is alleviate some of that torsional strain around the ring. So this is how 5-member rings deal with this. They're very popular in nature. They have pretty low strain energies here. Again, 20 kilocalories per mole. They can overcome this. And the thing that I think is so cool about 5-membered rings is you're going to find them in all sorts of compounds such as steroids and drugs because they can accommodate and make at least one carbon tetrahedral and the others almost tetrahedral. So they're very popular. All right, what about cyclohexane? So take your model kit, break it apart, and add one more carbon to it. And let's make cyclohexane, one of the most popular rings and the most stable rings in all of Orgoland. So cyclohexane is very stable, but not as shown here. Planar, flat. This would be awful for a cyclohexane because torsional and even increased bond angle strain, because it's getting further away from 109, it's going to 120. So cyclohexane has to alleviate this by doing things similar to making an envelope. It actually does all sorts of other things. It does 2 things in general to reduce the torsional strain and the angle strain. Okay, and these two general low energy non-planar conformations are wonderful for a cyclohexane. So let's see if we can try to build them, show them on a two-dimensional slide here, and then live through my little models and your model kit there. So let's start with the boat conformation. I love the names of these two conformations because they actually represent the shape that these molecules want to attain. So it's a little less stable due to some steric hindrance, which I'll show you in a second, but this is what a boat conformation looks like. It takes each end of the cyclohexane ring and bends it up, okay, so that they are no longer in the same plane as the other four carbons. And so this relieves a lot of torsional strain energy, tons of it. It also allows for these carbons to become tetrahedral, okay? The only problem with pulling it up like this is, as you can see on the diagram, these two red hydrogens in the structure look very far apart from one another, but in all honesty are very close together. And therefore, these are called, here we go. These are called flagpole hydrogens, or flagpole positions on our boat. And generally they cause a lot of steric strain, atoms bumping into each other. So this isn't perfect. This is better than planar, but relieving some angle strain, but causes a little steric strain. So let's look at the chair conformation, okay? The chair conformation. Oh, and to remind you what the boat looks like, just in case you haven't seen a boat for a while. There it goes. There's a boat. Okay, so let's look at a chair conformation. Whoa, what just happened? Okay, a lot more hydrogens got filled into this structure, but what I really want you to see is basically for a chair conformation, we have just taken the boat and taken this top end of the boat and left it as is, and then take this end of the boat and bring it not planar, but all the way down so that it is below the boat. It's like sinking boat, okay? And again, it's hard to visualize this as a chair, so I thought I'd show you a lounge chair. It kind of looks like that. Well, this is the head of the chair, is this carbon. There are four carbons that make up the seat of the chair, and then sticking down below here is the legs of the chair, or the footrest of the chair. So this is a chair conformation, and this is ideal. This removes any of that steric hindrance, steric strain that was taking place at the top of the two boat flagpole hydrogens. And now everybody is living in its own space, okay? This is such a popular idea. These boats and chairs are going to play such a critical role throughout all of our chemistry, throughout the course, that one of my past summer session courses decided to go out at the end of their course with some souvenir of their experience in their tour of Orgoland. So what they did is they created this t-shirt, which I thought I'd show you. And I think it just harps in how important this is this is what they took away from my Orgo course. That not only did they survive Orgoland and OChem, but they visualized it as a boat and a chair in the most extreme way. Like, yes, we're going to go lounge in the boat and the chair. So I thought that was kind of cool. But not the survival part. That's easy. This is fun. You guys are not going to have to survive this. You're going to be sad when your tour of Orgoland is over. Oh, you can always come back and visit. I swear. I'd love to see you guys anytime. So let's take a little closer look at this drastically weird looking chair. And if you don't have a model kit, please make sure to look online to look at other pictures and images of this chair conformation. But I highly recommend that you find some way to generate this chair conformation here where the top one is pulled up in the 6-membered ring, the 4 carbons in the middle are flat, and then this one is pulled down all the way on the other side of the boat, almost sinking the boat. And now I have a chair conformation. Okay? Let's look a little more in detail. When you create this chair conformation, there are 2 different kinds of positions for the hydrogens. As you can see, they've been color-coded here. That we have what are called axial positions. And I love that name because they are actually pointing straight up and down just like an axis would. And if you look carefully, every other carbon has a red hydrogen going straight up. So when you are trying to draw your chair or build your chair or imagine your chair, I often start by drawing the axial hydrogens first. They're all straight up and down. Okay? As you can see, and then every other carbon has hydrogens pointing in the axial direction straight down. So in any drawing that you do of a chair conformation, which I'll show you in a second how to actually try to draw one of these things, it's really, really important that your drawing communicates the 3 axial positions going straight down and the 3 axial positions going straight up, and that they alternate every other carbon. Okay? So that's really, really important. And then these 3 axials, you can just sit there and you can hopefully see that we have the head of the chair over here, the foot of the chair here, and the seat is the 4 carbons in the middle. This is putting all these protons in an axial position is not wonderful. There is a possibility of a little steric strain that they can bump into, but they're tetrahedral carbons in this conformation. So the angle strain is 0. So it really is beneficial for it to create this chair. Okay? Cool. All right. So keep in mind, axials can be on the bottom, and equatorials are all the other bonds that come out of the middle. Perfect name for it, equatorial. So when you go to put an equatorial hydrogen on or draw one, it will just go straight out. And so in your drawing, it's really important that I can see the difference between an axial, straight up and down, and an equatorial that goes straight out. It'd be great if you could kind of give it a 109 bond angle too, but I'm asking for the world there, aren't I? Woo, I want it all. Okay, sometimes we want it all. But this will come with practice. So how do you draw a chair? So this is a website down in little tiny print on how to draw a chair. What you're going to find is you have your own method of madness, as you'll see from mine. But really, drawing a chair is not easy. So let me show you. It just takes a little practice, and mine are just never perfect. I start with 2 lines parallel that are off center, and then I make the spike, the head go up, the feet go down, and now I have my chair. Then what you want to do is use this next image and notice the very first thing you draw in are the axial positions. And at the head of the chair, there's always an axial that's straight up. And then every other axial, you can draw that one straight up, that one straight up. Every other carbon is straight up. There's my 3 axials above the ring. Here are my 3 axials below the ring. Okay? And so those are the easiest positions to draw. It's really tough to draw the equatorials, especially on the carbons that are on the back of this 3D structure. And again, those of you who are used to drawing cubes are going to have a much easier time of trying to visualize this, because this is a front and back of an actual chair. And we kind of want to keep that in mind. There's a front that's coming out at us here, and there's the back side of the chair there. So practice. Please just keep practicing and make sure that I don't really care where your equatorials go. They could go this way. Again, that's kind of what it's trying to do. An ideal is it's trying to be parallel with this bond is this equatorial. But these are all axial positions. Okay? So how do we really make sure that we have a beautiful chair and that it loves to be in this conformation? There is one way to tell, and that is Newman, the cat. Newman projections. If we could draw a Newman projection down this 1-2 bond, you would prove to me that this big ring on one side and all these hydrogens at their axial equatorial, they are not eclipsed. If you can show me in a Newman projection that they're not eclipsed, then they're staggered, and staggered is great. And then the next thing that we're going to see is if you could make some groups on this chair anti to each other, that would even be better. So remember, gauche, staggered, those are all right. Anti is the best. Eclipsed is wah, the worst. Okay, so what would a Newman projection look like going down this bond? How do you even start to draw one? Well, remember, you always have a chest of the cat and a butt of the cat. So those are the first two things I draw every time. And now I want to turn my perspective kind of looking down that angle and try to put my mind's eye right down that C1, C2 bond, right? And if I put my mind's eye down that C1, C2 bond, then on carbon 1, I can see there is an axial red H that just pops right down, okay? And so right off the C1 here, the front carbon, I'm going to draw my first axial H, okay? And if you look at the back carbon, carbon 2, then up there, up there, carbon 2, as you look down that bond, you will see that there is an axial H that's pointing straight off carbon 2, which is the butt of the cat, the back carbon of this 1-2 bond. So the very first two atoms and bonds and lines, that you draw in a Newman projection should be the two axial positions when you're looking at a chair. They're just so easy to draw. Everything else is all over the place. But down a bond, there'll always be an axial up, one down, one up, one down in one way or another. Now comes the tricky part. 3D visualization a little bit. Here we go. When I'm looking down the 1-2 bond, I know that the rest of my bonds on my chest have to be in a tetrahedral geometry. And I know the rest of the bonds on my butt of the cat have to be in a tetrahedral geometry. My question is, though, where are those hydrogens that are equatorial attached? Where's that carbon chain, the whole rest of the carbon ring going to be? And therefore, I need to have a sense of perspective. If I'm looking down the 1-2 bond, that 1-2 bond is on the back of my chair, not the front. So it's on the back of the chair, not the front. And therefore, if I were to ask you, where is the bulk of your chair when you're looking down the 1-2 bond of your chair, which side on that axis, which side is the chair and most of the chair sitting at? Would you go to sit on the chair and go to the right of the 1-2 bond, or would you go to the left of the 1-2 bond? Yes, good answer. Hopefully you said you'd go to the right of the 1-2 bond, because that's where the bulk of the chair is. So on your Newman projection, I want you to write the bulk of the chair, CH2, 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 1, 2, 3, 4, 5, CH2. All of that chair has to be to the right. So carbon 1 has a CH2, it goes to carbon, 1 to 2 to 3 to 4 to 5 to 6, back to 1 again. So the whole chair wraps itself around on the right-hand side of my Newman projection, which means the left-hand side sticking even further away from me are the equatorial hydrogens. And I'm done. How did that feel? Again, a sense of perspective. Rewind me, go look at that again, hear it over, do whatever it takes. Take your model kit and look at it as well. So pull out and look down that 1-2 bond in the back and see all the rest of the chairs to the right and draw it to the right. The reason this is important is the chair is the bulkiest part of this whole Newman projection. And so what I want you to notice is that this axial position on the back carbon is gauche to the front carbon. Ring is gauche to the ring on the front carbon, right? And the same thing goes for the axial position on the front carbon. Notice it is gauche to the ring, the biggest piece. And so being axial is kind of tough because you're always gauche to the biggest ring. Notice if you're equatorial, kind of life is sweet. Notice this equatorial position on the front carbon here is, yep, you got it. It is anti to the ring. So putting groups, hydrogens, whatever, in the equatorial position, that position is much less likely to have any form of steric interference and steric strain because it is anti to the bulky ring. Okay, we're going to come at this again. So I tried to draw this in a prettier picture here. Hopefully you can see this a little better. But again, try to create Newman projections to help justify why chair conformations are so stable. Okay, nobody in these Newman projections, none of these bonds are eclipsed, and there's only a little torsional strain across the seat of your chair, but everything else is beautiful. Woohoo! Which is probably why my students love to put that on there. Okay. So let's ask ourselves, well, what if I have a hydrogen or a group or something that is axial to my ring and I don't want it to be axial? Well, here comes the magic. No magic, really. So here comes the story. You can take, let me make sure I get this right. Cool. Oops. I want to make sure my colors, oh, they are. Okay. So here is the chair conformation pictured on the left of the screen. It has a red axial here and a red axial pointing down. So the two red positions are both axial, one up, one below the ring, one above the ring. Okay. This is kind of nasty if I really want something in these two positions. So what the chair can do is it can actually ring flip. It can go through a boat, which means it actually pulls the feet of the chair up and temporarily has some really bad, steric strain, but then the top can bend not just down flat planar, but it goes past planar and goes back to the other chair. And so I can ring flip my chair and make the feet of my chair the head of the chair my feet. And when I do that, notice what happens to the red protons that were both axial now become both equatorial. Okay? So that might not be great because all of a sudden the blue ones are now both axial. But the message in this is that you can interconvert with a ring flip of only about 10 kilocalories per mole, which is not much at room temperature. And therefore, this molecule can ring flip from red axials to red equatorials all the time, back and forth, back and forth, back and forth. And that this happens thousands of times per second but this middle boat intermediate never sticks around for long. It immediately flips from one chair to another and creates this possibility. This will become important when we start to play with putting groups on our chair. Of course, I want to put groups. I want to put other things than hydrogens in the axial and equatorial position. I might want to put a methyl group on here and make methylhexane. So the question is, if I gave you methylhexane in this conformation with the wedge coming above and out of the board and the dotted line H, is this methyl axial or equatorial? How do you know? Well, you can draw it either way, okay? Because the molecule can do a ring flip, I can have that methyl start out equatorial, but if I pull that feet up, push the head down, I do a ring flip where carbon 1 all of a sudden becomes the head and carbon 4 all of a sudden becomes the feet. So ring flips can happen, and therefore I can get either one of these two. Now, we were just talking about which one should be preferred. If I had this big methyl group and I wanted to make sure that it wasn't bumping into the ring at all, as little as possible, then draw me the Newman projection down the C1, C6 bond, okay? This bond, as if you were looking here. And draw the same one down this bond, C1, C6. And again, keeping in mind which side would the ring be on as you're looking down that bond. Ring is going to be on the right or the left, who's on the front carbon, who are the axials, and give this a shot. If you did in these boxes, you would have found that this one with the equatorial, as we just talked about on the last slide, puts the equatorial, puts the CH3 that's equatorial and makes it go anti to the ring that's on this back carbon. Okay, and that is wonderful news. All right. Now notice I can't change the position of this CH3 to its own hydrogen on the front carbon, or even its position to its own ring piece that's there. But I can change the orientation of that methyl to the back carbon's ring. And that's why we like equatorial, because if you look at the one that has the wedged axial methyl next door, you will find that you get this position in the Newman projection, that this one is the axial that's pointing straight up, and there now it is bouncing right next to the back carbon's ring, the two pieces you had control over, and you put it in this one? No! So if you have a choice to draw the lowest energy conformation for a ring, you are going to try to draw this conformation. This is the one that would allow for the lowest energy, and this is the most favorable orientation, and therefore this ring is probably going to spend a lot more time over here, as you can see from the equilibrium arrows. It's going to spend more time with the CH3 equatorial than it is with the CH3 axial. Okay? And you can always argue this with a Newman projection. That's the part I like. You don't just have to take my word for it that equatorials are better. You have proof. We like proof in Orgo land. Okay. It is really loving it. So what if I did have other groups, or what if there's something this is really does bump into other things on the ring? These hydrogens here, these blue ones, notice it's gauche to these. That's not good either, especially if these start becoming CH3s. What are we going to do about all this? Well, one thing I want you to know is different groups have different effects. And what if I gave you a cyclohexane ring with different groups attached to it? A CH3, a benzene ring. How do you know, what if you could only put one equatorial and the other one not? How would you know which one to put equatorial? Axial strain energies. have been calculated for each type of group that you will see in this Orgoland tour. And this data table, which I highly recommend that you put on your 1 page of notes, will allow you to see that certain groups, like the methyl, here it was, have that 1.7 kilocalories per mole of axial strain energy. But if I put a methyl on a ring and also have a benzene ring, which is what pH stands for, is phenyl, a benzene ring, and you had to only put one equatorial and one axial, how would you know which one to put equatorial and which one to put axial? Well, I'd put the one with the highest axial strain energy equatorial. So I'd put the phenyl group equatorial and leave this methyl in its axial position because it's just a little less. And you can see that there are some that are just disastrous. You put this 1,1-dimethyl ethyl group as a group, otherwise known as a T-butyl group. Notice the shape of the T. You put that on your ring, and that baby better always be equatorial. That thing has such a big bulkiness that it'll crash into all the other axial hydrogens and make it for a disaster for that cyclohexane ring. So this is kind of fun in that you can design the most lowest energy conformation for any ring that you build. You can also design and let me know what the highest energy conformation would be, where we have all these axial strain energies. Okay? Take a breath. And let's play with more groups. Take a breath, go take a break. This is going to get even more wild and crazy, okay? But the idea is the same. The chair conformation is the best. But now when I have 1,2-dimethyl cyclohexane and I decide to put 2 methyl groups right next to each other on this ring, everybody do that. Put 2 methyl groups, 2 carbons, 2 whatever. Put them on the ring right next to each other. Okay, so here's my 6 carbons. Here's my 2 methyls. And notice I can put them right next to each other that way. Or I can put them right next to each other. And maybe you did this. One was on the bottom. Uh-oh. Hey, I warned you about this. Cyclohexanes can have cis and trans conformations. For these 2 methyl groups, I could put them both wedges, both on top of the ring, above the ring, and I could put them one above and one below, and therefore call them trans to one another. Nomenclature. Woohoo! So 1,2-dimethyl cyclohexane actually has 2 stereoisomers because it has 2 stereocenters. And there's no way I can take this trans version and just rotate because the ring doesn't rotate. There's no rotation in a ring. There's chairs that can flip one end up or down, but I can't literally break that methyl off and put it on top and go from trans to cis or cis to trans. Okay? So which one of these conformations do you think is happier? If you had to build 1,2-dimethyl cyclohexane, would you build me the cis isomer or the trans isomer? That's the question. Let's take a look. If I start putting these into a chair conformation, what I want you to really, really harp on here is that just because these are both pointing up and both wedges does not mean that they are both axial. This does not mean both axial. Or both equatorial. It's a very common misconception. So what this really means is that this methyl is above and on top of that hydrogen, and this methyl is above, that this methyl is above that hydrogen. They're both above, on top of the ring, above the hydrogens that are dotted lines. And when you then put them in a chair conformation, then one of these is going to become axial. And as you see in your drawing, the other one to be on top becomes equatorial. So if I were to do a ring flip to try to get this to move that top axial down into the equatorial and maybe see if I can move that equatorial and keep it there, I can't. Because the problem is, remember, when you do a ring flip, every axial turns into equatorial. On a ring flip, every equatorial turns into an axial. So everybody switches places, which means this molecule has no benefit to do a ring flip. It doesn't matter which chair conformation you have here. Both of them will always have one methyl axial and one methyl equatorial. Not disastrous, at least they're not both axial. Let's go look at trans. Please build these with your models. Definitely see them with the models and play around with them to make this clear to you. Let's play around with the trans. I can start with the trans and I can put, again, both methyls axial to each other. And again, notice trans, this was the wedge, this was the dotted line, this was the wedge, this was the dotted line. And so wedge methyl, dotted line methyl, these two, even though they look somewhat different on their two carbons, they are both trans to each other. And in doing so, they are both axial. Ah, both axial! Okay, well, quick, do a ring flip. Yes. Let's do a ring flip. And then both axials become both equatorials. And at equilibrium, what do you think is going to happen? Yes, it's never going to want to go back to the both axials. No, those babies are going to want to stay in the equatorials. So in our choice here of who is happier, the take-home message is try to get your actual groups into an equatorial position. Try to get as many, but this trans isomer is much happier than any of the other three forms because it'll stay predominantly in this form and keep both methyls in the equatorial position, which we know by Newman projections puts these methyls anti to the front and back parts of the bulky ring, the part I can control. So that's where you want to come at this. Again, constantly, please feel free to use Newman projections to argue. Again, drawing down this, looking down the bond here, this C1, C2 bond. If we were going to do this, should we do this? Okay, let's do this. Quickly, I would do this. The front carbon, carbon 1, has a proton that's straight down. The back carbon, the butt of my Newman, the cat, is got a tail that is straight up. That's a hydrogen straight up. I know that the rest are going to be staggered, so I start from this perspective, and then I look from where I am in 1 and 2. Where's the rest of the ring? It is to the right of me. So on the right of my Newman, I draw all the 4 other carbons that make up the big bulk. And then I have, on this one, I have methyls that are now equatorial. And so this equatorial back methyl is anti to the front carbons part of the big bulky ring. There's why equatorial, again, is a favorable thing. So please keep using Newman projections to help show how two groups can actually prefer to be equatorial. All right, we started 1, 2. Let's go the full gauntlet. Let's try 1, 3. And this seems like if we just did 1, 2 and you had to draw out all 4 of these chairs, and you'll get very good at drawing chairs if you do that. but wouldn't it be nice if I could look at the cis isomer and the trans isomer, and you could tell me without drawing out all the chairs, which one of these would be the preferred actual lowest energy conformation for 1,3-dimethyl cyclohexane? Wouldn't that be nice? You're going to thank me later for this. We can generate a mnemonic that you will want to write on the first page of your exam or on your notes, because this mnemonic will allow you to, no matter where the groups are attached on this cyclohexane ring, you will be able to tell where you want to put these groups, like the two methyls. And the way this is done is due to the fact that, if you remember, every other carbon had an axial sticking straight up. I had 3 axials coming up above the ring. So every wedge above the ring, every other carbon is a wedge, and every other carbon is an axial, which means that every other wedge has to be an equatorial. Now, granted, I could also show you the dotted lines that underneath these, every equatorial has an axial. That's a dotted line. And therefore, below that equatorial is an axial pointing straight down. Now you can decide, where do you want to start and add one of these methyls? Now, remember, we like methyls in the equatorial position. So I would put the methyl here. There's a wedge methyl on cis. And what if you put the wedge methyl here? That means the other methyl on the cis has to go here. And so this is the cis conformation, would have both of these methyls in the equatorial position. Woohoo! If I made one of them a methyl dotted line, like this one on the bottom, sad, sad news. If I looked at the trans and kept this top one methyl equatorial, the 1,3, 3 carbons away, dotted line would be axial. So keep this in mind when you're looking at your chairs. Every single group on the top above alternates between axial, equatorial, axial, equatorial, axial, equatorial. Okay? And therefore, every wedge coming above the chair alternates, and if you have a choice, put your methyls equatorial. Okay? How's that feel? So you could have those 2 methyls diaxial, do a ring flip. Are you crazy? Why would you do that? Okay? Or keep them both equatorial. Or you could do the trans, where you could have 1 axial, 1 equatorial. Don't want to do that. So in all honesty, what happens in the end here is, yay! We love the cis stereoisomer. And if I ask you to ever draw me the most stable conformation for 1,3-dimethyl cyclohexane, you should immediately go to your mnemonic, see where you want to put 1 and 3 to make them both equatorial if you can. Okay? And this can be used whether they're 1, 2 next to each other, 1, 3, 1, 4, all the way across from each other. That's the numbering we use on a cyclohexane ring. How's that feel? Well, let's see. This is where it goes. Why not? Let's play with phenyl and methyl and put them on opposite ends. And you tell me which one of these structures is the most stable, and maybe there's more than one. Ooh, tricky. Flip the ring over, ring over, ring over. I don't know. Tricky. But what I'd love for you guys to do in trying to show your answer for our study group is, let's start doing more than just coming to the study group hoping that somebody in the group has an answer to this question that you'll be willing to see. You be the person, and everybody's now going to be the person, because I want you all to take a picture of your drawing of the C1, C2 Newman projection down the conformation of whatever answer you picked. to show me which one it is so that you can prove to yourself, to everybody in your group, post it in our Jamboard, and let's see if everybody has the same Newman projections for the same compound that you all agree should have the lowest energy conformation. And that's what I want to see in our Jamboard coming up. Okay? All right. You've done great. This is as complicated as it gets. We can start throwing more and more groups on the ring, but you have the mnemonic. You know exactly where you want to put them. And life is gorgeous in Orgoland. It's a beautiful day. You too will survive Orgoland. I mean, have fun in Orgoland. And I will see you in class soon. All right. See you guys. Please feel free to send me any questions. I love questions, as you know. Okay. Bye.